So in the first section, I want just to get from discrete systems to continuous systems. So discrete, continuous. And we have seen the Fibonacci sequence, right? What we had there was xt plus 1. Let me write this a little bit differently. Minus x of t is equal to x of t minus 1. So this is a dynamical system. Oh wow, yeah.
You did, right?
Wait, what?
Yeah, Winthrop.
You got Winthrop?
Wait,
No, you got Lowell.
Oh.
Winthrop.
yes, Winthrop. We can jazz that every night.
Yes.
We can
Yes.
actually
Wait,
jazz.
wait, Julian. Julian's a really good trumpet player. Jazz. I did the same.
Oh, yeah.
Winthrop jazz band.
Wait, you also know Winthrop?
Yeah. We're in the same walking group.
Oh, okay. Well.
Is this it for today?
Welcome. So we are discussing differential equations. Oh, not yet. We are discussing dynamical systems. And if you think about this as a derivative here, so this is kind of a discrete derivative. Because it is a rate of change. The rate of change, we can just, instead of taking this discrete change, we can take a continuous change, and then we can say d over dt of x of t is, and then the t minus 1 is essentially the same, then if the time step here is very small, so we can look at this differential equation. This is an example of a differential equation.
Hey, Oliver.
Yes.
Which side represents the discrete derivative? Is it the left side or the right side?
That's the left. That's kind of a discrete derivative. Some people write here d delta xt or something like that. It's the rate of change. It's a discrete rate of change.
Oh, I see.
And so if you think about it, graphically, right? So this is time. Always we think about t as time. T is always equal to time. And what we have is if you have x of t here, if this is a time t and then a time t plus 1, what we actually do here is this is the rate of change. This is the delta x of t. And now we change if this delta, if this t goes to t plus 1 is very small.
You got low?
Congratulations.
So if this is very small here, you think about this as a rate of change. So this becomes a derivative, and so this equation is an example of a differential equation. Example of a differential equation. And it's called an ordinary differential equation because only one variable is differentiated with. So more precisely, it's called an ODE, which stands for ordinary differential equation. Because it's such a long word, we like this abbreviation ODE, and this differential equation is somehow a continuous time brother of this Fibonacci difference equation. This was actually called a difference equation. And this is our differential equation. Now we learn how to solve this. If you would not know, but you probably know the solution of that. What is the solution of this?
E to the
t. That's right, e to the t. So this is solved by, we know that this is solved by.
Wait, Oliver, do you have outlines?
Oh yeah, I have. Oh yeah.
Let's go.
I may not
I'll get
be
you guys
playing this, so I was very optimistic.
Wait, how many did you print? 20.
Oh, so this is solved by x of dt is e to the t. That's a solution. Do you see another solution? There are more solutions than this. 2e to the t. We can take any constant c times e to the t. So that's exponential growth, measures exponential growth. And I can just tell you that this differential equation is by far the most important differential equation. And everything we do in linear algebra, the rest of the course, until the very end when we do partial differential equations, we always will reduce it to a differential equation of this type. So more generally, when we have a d over dt, x of t is lambda x of t. So if this will be an eigenvalue here, we will look at it already today. If this is an eigenvalue, this is solved by, what is the solution of that? E to the lambda t. Solved by e to the constant times e to the lambda t. Now, it depends very much whether lambda is positive or negative. If lambda is positive, then we see this exponential growth here. And if lambda is, this is x of 0. If lambda is negative, then we have an exponential decay. So let me just make here a picture. I hope one still can see that. So we have x of 0. That's actually our constant here. So that's x of t, and that's x of 0, because at t equal to 0, that's equal to 1. So this constant is actually just x of 0. And now we have two possibilities, or three possibilities. Either we have lambda positive, then we have exponential growth, or we have lambda negative, and then we have exponential decay. And that's also important, like in a radiative decay. And then we have the third possibility is that lambda is equal to 0. So it's very important that we have this really dramatic change here. And for us, this lambda will be always then the eigenvalue here for us. So everything we will reduce to this equation. So that's why this equation is so important. Essentially, if you understand this equation, you understand everything we do in the rest of the course. So that's very important.
How can a function have an eigenvalue?
What we will do is we will look at systems of equations where this will be an eigenvector and this will be the eigenvalue. So when we have x of x is equal to, so ax is equal to lambda x, and we will look at, that's why we look at this today, x d over dt x is a of x. Then if we have an eigenvector, we will reduce it to that, and then we get this.
Okay.
But we will come to this. This is part of today's lecture also, to understand this relation between systems of equations and this. But I really want that this is clear, this exponential growth equation, which we have seen here also. We have saw an exponential growth, but it was not e to the t, it was square root 5 plus 1/2 to the t, essentially. So it was a little bit a different growth rate, but qualitatively we have the same behavior, this exponential growth.
Hey Oliver, for that one over there, the c e to the lambda t, how come the lambda t, isn't it supposed to be, how is that a solution?
So when we take the derivative of this with respect to t,
oh no, but then isn't lambda going to keep being nth rooted or something?
we take the lambda out here.
Oh,
So
we just
this
care
is
about the first derivative.
Yes, we take the first derivative. Yeah, that we will look at the second derivative too.
Also, we just care about the first.
First, yeah,
Okay,
that's the
okay.
first. So that will be when you have the square root, and we have the oscillations. So we will come to this. We have a whole week about this. But first of all, here we have just this. This differential equation is solved by this exponential growth or exponential decay equation. Let me just at this point also introduce a little bit of notation. This is a kind of a long-winded way to write the derivative because it's such a long-winded way. Leibniz introduced another notation. So we have instead of writing always d over dt x of t, we just write x prime of t. This is Leibniz. And Newton was even more efficient. How can you even make it more efficient than writing a prime?
You just write a dot.
Stop.
Why?
That's Newton. Actually, both. Leibniz usually won in the notation. He has great notation. But Newton also, this notation is often used in physics. So it's still an important abbreviation. Good. So that's the first section. How we get this? How do we get this exponential growth from a discrete system? But let's assume we don't know what the solution is of this, and there's a method which gets you solutions to any differential equation, even nonlinear differential equations. This is called the separation of variables method. Did you do that in calculus?
Yeah.
Did you do it?
At least in 1B. I don't
Good, very good, very good. That's it's a very important method. It's actually pretty cool. So what you have is, what you do is you just write this as, just write this as dx over dt is equal to, say let's take 22x.
Aha!
Which was that number?
Where does that number come from?
Why, of course I don't. Huzzah.
So we have that. And now comes the idea. What we do is we put everything with x, we put on this side, and everything with t, we put on that side. So we separate the variables. So what we have here is we have the dx over x is equal to 22 dt. Some way this doesn't make sense, right? Because these are kind of just symbols, but it works. And what we can do is then we can just integrate on both sides.
Can we use the fundamental
Can we
theorem of
prove
calculus?
this?
What?
We're going to use the fundamental theorem of calculus?
Essentially, well, that's what we do.
Yeah. Why can you just separate the dx dt like that?
Yes.
It's just
I think it's just
Can't really.
mathematically, it's just.
I mean,
you know,
I know it
it's
works.
just essentially kind
Like,
of
can we-
nonsense, but it works. It's kind of a method
Can we
which
prove
just.
it?
What?
Can we prove it?
What happens is once you have a solution, you don't care how you got it.
Apply that for you.
Apply that, let's go.
Well, so like,
So once you can check here that this solves.
Oh, I see what you mean. Yeah.
So you can check that this solves it. So you don't care how.
So maybe you're gonna
with
get a
what
log.
magnitude.
That makes
Yeah,
sense.
You're gonna get a log, though. You're not gonna
Wait,
get
well,
exponential,
Oliver,
though,
how
right?
do you know that's the only solution?
how do you know you're infinitely small?
that's a good point. And actually, did you see there? This is in general not true that you have only one solution.
No, like how do you know,
Even
even if you
solve-
do general solutions, how do you know that's the only one?
Good question, and actually it's a very, I mean, in general, very tough question. Say for Navier-Stokes, when you look at the weather equations, you don't even know it, and you get $1 million just to prove that there is only one. So it can be a really tough problem. And in the case of this equation here, there is just one. And there's a theorem which says which equations give this. It's the
Not the external.
Hey Oliver.
Yes.
So applying this separation of variables, it depends on the fact that the integral is trivial. Or at least it's
Yeah, in this case we can just integrate. What is the integral here?
ln of
ln of x. Okay, so we have ln of x.
Natural.
That's 22t plus c. And so now we can solve it by, how do we solve for x?
exponentiate.
Exponentiate, so this is e to the 22t plus c. And this c is actually just, you know, we can take e to the
A,
c,
right?
can just write it as e to the
But it's not the same C though, right?
It's not the same C.
C prime.
So that's kind of a little c and that's a big c.
But it's still
So that's a small c, that's a big capital C. So that c is just e to the small lowercase c. So that's how we do it. Let's just practice it in a little bit in a different. This works very general. This is very general. let's look at another system. Let's look at dx over dt is equal to x times 1 minus x. So you might have seen this also. If you have studied a little bit of differential equations, you have seen this. It's a very important system. Somebody know the name? Sure, you have heard about it. Logistic. Very good. This is the logistic system. And it's very important in population dynamics also, because what happens is this exponential growth is not sustainable. You cannot grow exponentially for, t equal to 100. This just doesn't make sense here. It's just too big. Populations will run out of food, for example, and that takes care of this. So this is actually just x minus x squared. And so what happens is when x is equal to 1 here, you usually put a constant like m. When x is equal to 1, what happens is the population has slowed down. So this is say m equal 1 here, if this is constant m. And what happens is that if you start here with x of 0, you start here, it will grow exponentially at first for small t, because that x squared is very not relevant yet, but then it will eventually slow down because the slope here, this is the slope, this is x prime, this is the slope of this graph here will go to 0. So the solution will look like this. And I don't know whether, if you have done differential equations, you probably draw these slope fields here. And study this a little bit. But let's just try to solve this with our method of separation of variables. So what do we do when we do the separation of variables?
We separate.
We separate. It's such a nice method. We just separate everything. So we get dx over x times 1 minus x is equal to dt. And that's no problem to integrate. Even so, I noticed that this is no more taught so much how to integrate this kind of. I wonder, does somebody know how to integrate this?
DT.
How do dt is that's
Nobody teaches me how yet.
Could you partial fraction decomposition?
I'm so surprised that this is still, because this is usually no more taught. I think it's no more taught in 1B.
It's on like calculus BC.
It's on the BC
It's
exam.
on the AP calculus.
Yeah, it's very important. It's just
no one
it's
gets
just
that.
algebra, right? What you do is you just write 1 over x times 1 minus x. Right? You write it as a over x plus
D over
d over 1 minus x, and then you figure out what the a and b are by just cross multiplying. In this case, it's just 1 over x plus 1 minus x. So this is called partial fractions. It has actually nothing to do with calculus. It's actually algebra, because what you do is you write a rational expression in terms of these Egyptian fractions. So this is algebra. But now we know how to do that integral, right? So we know how to integrate dx over x times 1 minus x. What?
No, sorry.
So what is it now? So we have a
Natural log of x minus the natural
exactly
log of x.
exactly 1 over 1 minus x. So we get the natural log here. So this is the natural log x, and then minus the natural log of 1 minus x, which we can just write as the natural log of x minus 1 minus x. So that's the integral of this. First, if you look at it, it looks tough, but it's actually possible with this partial fraction. And then we have this equation, right? We have ln of x over 1 minus x is equal to t plus c. And now we can do it. We say x over 1 minus x is e to the t plus c, which is, now we have to solve for x. So x is equal to e to the t plus c times 1 minus x. Then you can solve for x. I think I have to use another blackboard so that one can look at that.
This is much more peaceful than differentials. This is much more peaceful than differentials.
Someone have a water bottle by chance?
Yeah, I can hit you.
I could get some white.
Oh, if you have some, that would be great.
Let me just,
I did not bring mine, unfortunately.
The
Thanks so much.
Just look at the yellow white is 0 as x approaches.
X approach. But why is that slope? Why is that y? Like, why is it asymptotic at y equals 1?
Because when y equals 1, or when x equals 1.
Like you drew that n equals 1 line, and then it's asymptotic for that. How is it?
Good. Oh, because that's an arbitrary y. So like when you have x equals any number of 3, or any, as it gets closer to 1 minus x is 0, so the slope is 0. So you don't reach a slope of 0 until you get x gets close to 1. Once x is close to the 1, so before x equals 1, you have nearish 1 number times nearish 1.
Why
That doesn't make any sense.
Why is that like horizontal asymptote y equals 1?
Because what happens when you are here, the rate of change is 0.
Right. When
But when
x
x is equal to 1, then your rate, so you don't decrease and decrease. So this is actually a solution. If you start here, it is a solution.
wait, isn't that y is 1?
Actually, I see what you're. Notation is quite a bit of a thing. Usually, what you have seen probably in thing, you wrote like that. Y prime is a f of x,
Yeah.
right? So you use x as the variable and y as the
No, T.
dependent
Oh,
thing.
okay.
Now we use t as the variable and
Okay.
x as the.
Okay.
So it's a little bit. Notation can be a little bit. Actually, sometimes we will use x. Sometimes we will later we will use also f. So. So you have to get used to, and sometimes we use x as the variable as the and not t.
Why?
So it can be. The reason is because later we will look at partial differential equations where the rate of t is time and x is space, and both will matter. So both matter, space and time matter.
Really?
But now we are almost finished here, so we actually can solve this for x, right? So we see that x. So what we have is x. We take x on one side here, plus e to the t plus c x is equal to e to the t plus c, and now we can solve for x. X is equal to e to the t plus c over 1 plus e to the t plus c. And you see that actually makes perfect sense, because what happens when t goes to infinity, by orbital, that goes to 1, right? So that goes to 1 for t goes to infinity by orbital. Just bring me to the hospital. So that's the, and we can solve many systems like that. But Maxwell had a great kind of question here. Let's look at this equation here. Let's look at this equation here. So this equation, when you look at this one and you solve this, this is another example. When you solve this, you see dx. Why don't you give it a shot? Just see whether you can kind of see whether you get the same thing. Over x squared is equal to dt. You might actually just see without even writing down. But then you see x of this. You see 1 over x. We integrate that. Dx over x squared is equal to dt. So we see minus 1 over x is equal to t plus c. And so we get x is equal to minus 1 over t plus c. And so yeah, you see what happens is actually, in general, this has a problem at t equal to minus c. So, so what happens, say for example, if we have x of 0 is equal to, so if x of 0 is given, like x of 0 is equal to 1, for example, we can solve for c. So that's also here. We could, given x of 0, we could actually find the constant c. And also here, when x of 0 is equal to 1, what is c? So when you have 1 is equal to minus 1 over 0 plus c, you see that c is equal to minus 1, and you see that this is actually x is equal to 1 over 1 minus t. So that's an interesting equation. It tells us that at t equal to 0 we have 1, but then what happens at t equal to 1? And that's time. At t equal to 1 you have gone to infinity. So these differential equations usually don't have existence of solutions for all time, and so we can have blow up of solutions. And one believes, for example, for the weather equation, for the Navier-Stokes equation, that such things happen, that you have kind of maybe some things which develop problems after some time.
Good job.
And but it can be even worse. We can have no solution. We have more than one solution. Let's look at this example when we have dx over dt is equal to. You have also homework about that. If you look at this equation, this looks harmless, right? But if we do the separation of variables, we get trouble. Okay, what is this? What is the derivative? What is the integral of that?
Very ugly.
Square root of x
Negative square
Minus-
root, minus 1 half.
2 times square root of
Is
x.
it negative? No, it's
No,
not.
it's positive. 2 times square root of x is equal to t plus c, and you see that x is equal to t plus c half squared. Looks good. Looks good. But we have another solution. So we start with x equal to 0, so that's actually pretty nice parabola, right? And c is equal to, say we start at 0, then c is equal to 0, so this is actually just t half squared. It's a very nice solution. And you can check that, right? So if c is equal to 0, this is t half squared. You can check that, that's t squared over 4. When you take the derivative of t squared over 4, you get t half, and t half is just the square root. So that solves nicely this problem here, that taking the derivative of the function has the property that it's equal its square root. But there is another solution, which is kind of vexing. So we have also x of t is equal, does somebody see it? It's hard to see.
Is it the negative one?
No. Oh, that's a good point, actually.
Because you could have minus t minus c squared and have the same.
Some sense, because, but then you get negative square root here.
Okay.
So you would just have to take the real part, or. But there is another one which is kind of vexing. This is really vexing. But it's hard to find because it's so easy. The easy things are hard to find. Does somebody see another solution?
Is there an ln
One.
effect? No.
ln
0.
0. Very good. Oh, cool. Very good. Yeah. So if you take that, that's also so what we have is we have two solutions, and actually that's exactly your question, right? So do we have a unique solution? And actually the answer is in general not. There is another solution. X of t is equal to 0.
Hey Oliver, how did we arrive at that x of t equals 0?
Because it,
Oh, we just, intuition. Roscoe just had the intuition. Yeah, why not just try?
because it works. If x is 0, then the square root of
It
0
stays
is always
0, right?
dx dt is 0, and 0 is 0 is 0 is 0 is 0.
So it's kind of vexing that you have systems of it, or that is differential equations might not have unique solution. But the problem is that the derivative of this is not. So what we have f of x. There is a theorem of Peano which says, or which says that, that there is always a solution if f prime is bounded. Or if f is Lipschitz. We have talked about Lipschitz briefly. So there is a kind of there's a theorem which tells you when you have solutions, at least for a short time. But that's all I wanted to say. You practice this a little bit, and that's all what I wanted to say about differential equations in general. And what we do in this course mostly are dealing with linear equations, and that's what I want to do next. So systems of linear dx over dt, and it's linear. Let's assume, for example, we have 3x of t plus 4y of t. So there are two x and y, two variables we are interested in. So what I want is maybe 6x of t plus so what we first of all, there are two changes. So we have a system of equations. And you can also write this in vector form. So if you, for example, would write v of t is equal to x of t, y of t, and we can actually write this as dv over dt is equal to a of v of t. And what is a? Where a is a matrix.
3, 4, 6, 1.
Exactly, that's just a coefficient matrix. 3, 4, 6, 1. So we can write this in vector form. In vector form. And you see that looks really like that problem we had before. dv over dt is lambda v of t. Right, and actually you can. It's no change, and this has a solution. It has the solution. This has the solution. V of t is e to the at, and you can just do the same thing. Instead of a number here, why not just take the matrix? And if you take that matrix, so what is this? This is 1 plus at plus a squared. T squared over 2 factorial plus a cubed t to the 3 over 3 factorial. And you can double check that if you take the derivative of this, right, if you take the derivative of this goes away, this becomes a. What happens when you take the derivative? This becomes a. This becomes 2t over 2 factorial. That's just t times a squared. And you see that it's just a times what you ended up. By the way, that's another way how to verify that e to the lambda t solves the equation x prime is lambda x by just writing down this Taylor series. You can see, when you differentiate it, you get the same thing back, just multiplied by lambda, and here multiplied by the matrix A. So, but the problem with this is that this doesn't give you a lot of insight what is actually going on. So this is a solution. This doesn't give us insight. This solution doesn't help us. So we want to understand, for example, what happens here in the future. What happens at time t equal to 100, and how does this grow? And we have seen already, yes.
How did we get at that again? Sorry, I think I missed that.
Which one? Which step from here to here, or
from the one
from
on
here to here?
From the left side to the right side.
Yes, that's an important thing. So when you look at this and you look at this, it's like systems of equations. When we solve systems of equation, we had coefficients here. So these coefficients here is actually, when you look at one here, this is the coefficient matrix. If you just write this down here, if you take this matrix and multiply it with x, y, what you end up is with the right hand side.
So A of t is, or A is the,
A is that matrix,
what do you call this? The,
coefficient matrix.
not coefficient, is it like a differential matrix or like
I
differential?
don't know whether there is an official name for it. It's just a matrix which is giving you this differential.
Oh, but the coefficients in there are the coefficients of the rate of change.
Yes, they exactly. These coefficients are here in that. By the way, you have some great problems in the homework, which are not so easy, but they are from Otto Bretsch. One of them is from Otto Bretsch. It's a slamming door problem. It's kind of a beautiful problem where you see, in order to get some insight, it also helps to draw it, and we will actually do that here. And when we draw the phase portrait. For now, we just are concerned with solving this system of equations. And so this is similar in the, so we do the same thing. The discrete version. Remember the discrete system? We had xt plus 1 is equal to axt. Remember how we solved this? Remember how we solved this?
We made a vector. X of t or x of t.
But yeah, we had the eigenvalues. We looked at the eigenvalue here. That's what we also do here. We had an explicit closed form solution. That was the last lecture solution. And then remember what we had? We had x of t, and then we wrote x of 0. We wrote x of 0 as c1 times v1 plus c2 times v2, where these were eigenvectors, and then we could get x of t by just every time you apply a, you get the lambda to the t. This is lambda 1, and then this is c2, and then lambda 2. Might be too low here to be seen. Essentially, my bear cannot see, definitely not see. So, so we have that. That was the closed form solution. There's also a closed form solution here. Very, very similar. So if